Yeah, so this is a result that we had sort of sketched an idea for a proof almost a year ago, and then in the spring, just before I gave a talk on the material, I found a significant hole in the arguments, and so this is we're at the point where we feel like we've essentially patched the hole, but yeah, the arguments are still not as pretty as we would like. But let me give you an idea of what we're doing. So I'll start off. So the outline of the talk, I'll start off talking about uh, embeddings of an n-dimensional disk into a circle across a disk, and pi zero path components. And there's an argument that that's a group always. Uh, so I'll start off with why that's a group. It gives sort of some of the flavor of some of the tools we'll use. And then the main plot is we construct some elements in the n minus second homotopy group of the space of embeddings of the circle into S1 cross Sn by taking an immersion with a singular or with a single regular double point and doing a resolution construction. So very much like Vasiliev's perspective on embedding spaces, and it gives some elements of pi n minus 2. So this is interesting when n is 3 or larger, uh, and then we use a fibration to turn those elements in the n minus 2 homotopy group of the embedding space to diffeomorphisms, but one less parameter, so pi n minus 3 diffeomorphisms of a circle across a disk. And so we're going to call those elements theta k hat. And then the sort of the core of sort of fixing the problem that we had that we noticed in the spring is so we want to show that those diffeomorphisms are non-trivial. And what we're doing is we think about what the diffeomorphism does to you know a point across dn. So that gives the diffeomorphism will re-embed it, and then we do this construction that we just call fibering, where you think of dn as an interval across a dn minus 1. And from that point of view, this embedding produces a element of the n minus first loop space of the space of embeddings of an interval with the endpoints fixed on the boundary in S1 cross dn. And usually those maps, I wouldn't usually consider a map like that, because in my experience, those maps are almost always null and not interesting. But we have an argument that that this map, it's actually detecting these embeddings. So that the argument, I think the argument is rather surprising, and because it's surprising, I think it should be held to a pretty high standard. I've got an argument for you today, but you'll see it's rather delicate and geometric, and it probably deserves to be put on a broader footing that more people are going to find pleasant. In part 3, I'll supply the sketch that is non-trivial. So basically what is going to happen is I'm going to chase through all these constructions rather explicitly, and I'll be able to just show you in a diagram what that element of the homotopy group of this embedding space is. And so I'll be able to describe it as just sort of motions telling you where the strings move in that family, and then we'll invent an invariant to detect it. And in the last part of the talk, which will probably be the last 3 or 4 minutes, I'll talk about relations to the smooth 4-dimensional Schoenflies problem. So we don't give a counterexample, but we give something that sort of it's sort of a, it's really interesting and non-trivial, but not a counterexample. And this also relates to the homotopy type of the space of the unknotted embedding of S2 and S4, that will show that that doesn't have the homotopy type of the linearly embedded subspace, like the great 2 spheres in S4. So that's the outline, and I'll come back to the outline every once in a while. But so this concept of a reducing disk, so that a reducing disk in a circle across the disk, it's a smooth embedding of dn in S1 cross dn. That's the standard inclusion on the boundary. So you just take point 1. So I'm thinking of that as sitting in the complex plane, the circle in the complex plane. So the space of reducing disks we denote with this embedding space terminology. So the main goal of this presentation is to describe why pi 0 is a group, and to describe why it's not finally generated when n is 3. Here's the argument, and it's sort of cute arguments that they seem to go back to Cerf. So we take the n-dimensional half disk to be the intersection of the standard n disk with a half space. So HDN means all the vectors in Rn, norm less than or equal to 1, and the first coordinate is less than or equal to 0. So the intersection with the boundary of the disk is called the round boundary of the half disk, and the intersection with the half space is called the flat boundary. So the space of embeddings of a j-dimensional half disk in an n-dimensional half disk, that means all smooth embeddings, and they agree with the standard inclusion, but only on the round boundary. And these spaces of embeddings are contractible by uniqueness of color neighborhood argument, sort of the parametrized version of the uniqueness of color neighborhoods argument. You just sort of shrink it down to the part where it's standard. Yeah. Okay, and then you linearize. I mean, it's a subtle argument, but it's fairly standard. So a theorem, I believe it's well, he didn't state it this way, but it's essentially due to Cerf, that there's a locally trivial fiber bundle, and the total space is the embedding space of this j-dimensional half disk in Dn. And what you do is you restrict that embedding to the flat face, the flat boundary component. So that gives you an embedding of dj minus 1 into Dn, which is standard on the boundary. Not only that, it doesn't give you every embedding, it just gives you unknottable embeddings. And I want more than just that embedding. Let me maybe bring a picture in here. You've got here's a 2-dimensional disk embedded in the 3-dimensional disk. When you restrict that embedded 2-dimensional disk to the flat boundary, there's a unit vector field, the sort of the outward pointing derivative. The embedded in this case interval together with that vector field, you could think of it also as an embedded little ribbon, like take a little neighborhood of that flat boundary. Anyhow, so that's what the plus indicates. This you have this unit vector field along the embedding. So that's a locally trivial fiber bundle, and the fiber has the homotopy type of the space of embeddings of dj into a sphere across dj. And basically the argument for that is the fiber, it's standard along that flat boundary and the regular boundary, and the derivative is standard. So with a little bit of an argument, you can demand that it's standard in a neighborhood, and then you blow up that boundary half space, and you've got an embedded dj and a sphere across dj. So that's why you have that relationship between embeddings of disks and embeddings of disks in sphere across disks together with embeddings of unknottable disks in disks. So you get this corollary that the space, right, that the total space of that fibration is contractible. So the what is this? This is the fiber. It has the homotopy type of the loop space of the base. And so pi 0 of the fiber, it's always a group from this homotopy equivalence. But there's also a monoid structure. Well, if you want, there's an operand action, but there's a monoid structure on this embedding space coming from, you've got a disk and a sphere across a disk. You can just stack 2 spheres across disks on top of each other coordinate-wise, using half of the disk, identifying half of one disk to the half of the other, and using the identity on the sphere factors. So this is a stacking operation that turns this into a monoid, and so under the equivalence that gives you 2 operations on this space, and so by a sort of a standard Ekman-Hilton argument, they're the same. So yeah, anyhow, that's why pi zero of disk in sphere across a disk is always a group. I found that really informative. I didn't know that was true. Like every example where I knew pi zero, it just seemed to be a group, but I didn't know why. Like I didn't have a general argument. Anyhow, so relations to other theorems. So there's this theorem of Hatcher and Wagner that pi zero diff of S1 across a disk, provided you're in a very high dimension, it splits as pi zero of the ambient dimensional disk, pi zero of the factor disk, pi zero of diff of the factor disk, and then there's this direct sum of infinitely many Z mod 2s. So I'll mention, so there's a, well, I want to give you a slight reinterpretation. So there's a homotopy equivalence, and it, if you follow your nose, it's not too hard to prove. The diff of S1 cross Dn splits as a direct product, up to homotopy equivalence of diff of the ambient dimensional disk together with that space of embeddings. Basically, there's a fiber bundle and it splits at the fiber in a canonical way.
Fine, quick question.
Yeah.
Diff, real boundary?
Oh yeah, these are all the diffeomorphism groups I mentioned are going to be the identity on the boundary.
Thanks.
Yeah, that's and the only reason why I'm using that convention is that you get sort of flooded terminology. It'd be, yeah, I would find it rather confusing otherwise. Yeah, so from the perspective of this theorem, the Hatcher-Wagner theorem is saying that pi zero of embeddings of an n disk in S1 cross Dn, its natural group structure, there's the parametrization of the disk, and then there's the isotopy classes of images, which is the two torsion, and the group structure here comes from the stacking operation. So yeah, that's Hatcher-Wagner reinterpreted. And towards the end of the talk, I'll try to give you a conjectural way of detecting these Hatcher-Wagner disks. So yeah, back to the plot summary. So we're going to get families of embeddings of a circle in S1 cross Sn. Then we're going to convert them to diffeomorphisms. Then we'll do this fibering construction, and that's sort of where the bulk of the work is. So construction of embeddings. So you start off with an S1 cross a point in S1 cross Sn. Then you take an immersed half disk where the flat edge coincides with part of this vertical circle, and then the round edge wraps around the circle factor some number of times and then comes back and has that double point with itself. So there's a single double point. So they intersect. There's two one-dimensional manifolds intersecting in a regular double point. So the sum of the tangent spaces at the intersection is two-dimensional. We're in S1 cross Sn technically. Well, I'm thinking of it, Sn as the union of two disks. Apologies for that confusing notation there. But so that the span of those two tangent spaces is two-dimensional. The ambient space is n plus one-dimensional, so the complement is n minus one-dimensional. So the unit sphere is n minus two-dimensional. So there's an Sn minus two of ways of resolving those double points. Well, that double point. So that's the map that I call theta k. So you've gone k times around the S1 factor here. Yeah. So those are the theta k embeddings. And a theorem which is not too hard to prove is that these are linearly independent over the integers in that pi n minus 2 homotopy group. And so we construct invariants that separate these embeddings by counting regular double points of the projection to Sn map. So this invariant, so it's a Laurent polynomial ring. Well, technically it's a quotient of a Laurent polynomial ring valued invariant. And you could think of it as like the type 1 Vasilyev invariant, or if that's too old terminology from you, it comes from the second stage of the Taylor Tower for the embedding calculus.
So Ryan, could you
Yes.
say what you do to the double point again?
So we've got an embedding of a circle in S1 cross Sn. So you project that embedding to Sn, and it may not be an embedding anymore. So pairs of points that are sent to the same point in Sn, we call it double point.
Yeah, but even in definition of theta k, when you say resolve the double point, what do you do?
So you've got this pairs of points. Okay, we're back here so this is a double point in another setting because it's just an immersion here. So you take a little bump function. So you've got the parametrization of this embedded circle. And you take a bump function that's non-trivial, say only in this little stretch here for this, for the strand that goes this way. So the bump function is going to be 0 along this stretch and over here. So it's only non-zero in a little blushing area here. I'll define the function explicitly in a moment, but what we do is we add to it the bump function times the vector, the direction vector that we've chosen here, which is orthogonal to these two tangent spaces.
Say, Ryan, can I just try to say it another way?
Oh, yeah.
If you look at your picture literally, resolving that x is the usual thing. It's either an overcrossing or an undercrossing. And that's because in the literal picture, the normal direction to the x is one dimensional. So it has a circle. There are an S0. There's an up crossing and a down crossing. But in higher dimensions, that S0 becomes an Sn-2.
Yeah, exactly. So right, there's just in this picture, you could take that double point and you could move one strand over the other or move one strand under, and so the sphere, in our case, when n is 2, the sphere is disconnected. Well, in higher dimensions, it's connected, so you get some interesting stuff happening. Yeah.
See, thanks.
Good to hear your voice, Mike.
Hey, yeah, nice talk. Thanks.
Let's see. Yeah, so the argument is that they're linearly independent. It's this you count double points, and when you for this projection map for the family of embeddings, and when you have a double point, you can associate to it when it's regular in this transversality sense, you can associate a Laurent polynomial ring, technically quotient of valued invariant. And let me tell you how that works. So you've got so capital F is a family of embeddings. So capital F at V is one of them. And so here in this family, I'm saying I've got this point, the value at Z1 for that embedding and the value at Z2, they project to a common point in Sn. And so what I'm saying is, this is the first coordinate, because I'm calling it Z1. You sort of cut the circle at the double points, and at the Z2 you go down the vertical circle until you get to F of Z1, and so that gives you sort of a shortcut of the embedding, and that map now is no longer degree 1 mapping to the circle factor. You take the degree of that map. In this case, I guess it's degree 2. If instead you use the black arc and the red arc down, you cut it sort of the other way, the complementary way, I think you get degree 3. So what I was saying, you get a quotient of a Laurent polynomial ring, and it comes from this ambiguity because we're talking about embeddings of circles. They don't have like base points, so you can't choose which one to do first or second. There's a choice, so you get 2 possible Laurent polynomial counts for these double points. Yeah, so that's the description of the invariant. So Dax was the first to compute the low-dimensional homotopy groups of these embedding spaces, and he used sort of a souped-up Hafliger style technique, which was popular at the time. And Gregorone and Marcus Schimmick recently revisited this using embedding calculus techniques. They were after a different kind of result. David and I started giving things names, and Greg and Marcus were mostly interested in the infinite generation of the homotopy groups of these embedding spaces. So how do you construct diffeomorphisms from this family of embeddings? So given a diffeomorphism of S1 cross Sn, you can restrict it to S1 cross a point. So that's a map which just ODE theory tells you is a Serre fibration. That was proven by Serre in his dissertation, and then Palais went on to show that it's a locally trivial fiber bundle. So you get this locally trivial fiber bundle by taking an arbitrary diffeomorphism of S1 cross Sn, restrict it to the vertical S1 cross a fixed, a chosen point. That gives you an embedding here. So as a map, it gives you a map of spaces, and the fiber over a point is the space of diffeomorphisms of S1 cross Sn that fix whichever embedding you chose here. So if I choose the standard S1 cross a point, I would get diffeomorphisms of that type. Now, our family of embeddings, theta k, the way we chose them by resolving a double point, you can also make them embeddings that preserve a trivialization of the normal bundle. So not just an embedding of S1 and S1 cross Sn, but an embedding of S1 cross Dn in S1 cross Sn. And so if you take those fattened up embeddings here instead, the fiber would be the group of diffeomorphisms of S1 cross Dn, the complementary Dn to the S1 cross Dn in S1 cross Sn to fix the boundary. Yeah, so that's what I call the theta k hats. And now what I want to do is give you a way of thinking about the theta k hats. So these theta k hats, they're produced by an isotopy extension process of solving an ODE, right? The idea is that sphere of embeddings, you now, instead of thinking of it as a sphere, you think of it as a disk with the boundary collapsed. Now, once it's a disk, you can lift that family of embeddings to a family of diffeomorphisms of S1 cross Dn, and of S1 cross Sn, and and so those diffeomorphisms are they agree with the original embedding in that tubular neighborhood of the embedded S1. So you construct that family of diffeomorphisms of S1 cross Sn, and then you restrict that family to the boundary, and that's the diffeomorphisms of S1 cross Sn that fix an embedded S1 cross Dn. So the way you do that is, so here's our immersion that we started off with, and we resolve the double points. You can go between any one resolution and any other by a little motion in a neighborhood of the, basically you've got a little disk around that double point, and that disk is in every resolution. And so we can demand that our vector field that we use, it's supported in that disk. And so our diffeomorphism of S1 cross Sn, it's the identity everywhere except maybe in that little disk that we had the vector field in. And since our diffeomorphism was the identity on the embedding, a little neighborhood of the embedding, we've got a disk with two one handles drilled out. So that we call a barbell, an Sn-1 cross D2 boundary connects sum with itself. So that's our schematic depiction of the barbell. So what I want to do is just write down, you can write down a formula for that diffeomorphism in the barbell, well, technically in that blue disk. And so that blue disk, I'm going to amplify to being all of Rn plus 1 now. So you've got the original immersions, which in that blue disk is just I'm going to, up to a conjugacy, I'm thinking of it as the x-axis and the y-axis parameterized this way. And then here's that resolution construction. The resolution in the vector v of this family consists of that family plus a bump function in the v direction minus a bump function in the v direction, right? So that's the 0 function and the 1 function of this family. So you get a picture like that consisting of all these resolutions, and beta is some suitable bump function. Yeah, so now the diffeomorphism family, you can just write it down. Technically, this is not trivial in it's trivial on the on one of those resolved embeddings, it's not technically trivial in a tubular neighborhood of it. You have to do a little, you have to do a further isotopy extension to go that one extra step, but this is enough for us to work with. So this construction here is it's a holonomy construction for the tangent bundle of Sn minus 2. So I'm hoping you're familiar with the holonomy of the spheres. So it's like a differential geometry construction for getting at the clutching maps for the tangent bundle. But so I'll just walk you through what this formula is saying. So capital M is a mirror reflection. It's a mirror reflection orthogonal to a certain vector, and I've got a formula here. And so I'm composing two mirror reflections, and I'm evaluating it at point X in Rn. So I've got this is a sphere. So HV0. So there's an n minus 2 sphere, right? That's orthogonal to the that's the unit sphere. It's orthogonal to the tangent spaces at the double point. I've chosen a base point V0. I think I described that here. Yeah, that's a base point V0 for that sphere. And I've chosen a base point for the boundary of its hemisphere in that sphere. And so that boundary of the hemisphere is parametrizing the family of diffeomorphisms. And so what I do is I've got one point in there in the boundary of the hemisphere and a point in Rn plus 1. And this is a formula for how it gets transformed. You just push it through these two mirror reflections. And then which mirror reflection do you choose? Well, given that point W, you take the geodesic path from W to V0, and that's what I call gamma. And if I just use gamma of the length of X here, that would be a nice function, but it will only be piecewise smooth. So I have to use a little bump function that starts off 0 and ends up 1 to make it into a smooth parametrization. And yeah, so that this solves the isotopy extension. It pushes all those resolutions around the way we said they're supposed to. It is something to get your head around. I think it's important maybe to think about the NE3 case. The ambient dimension is 4. In that case, what this family of diffeomorphisms is doing is you've got that double point, and you've got that two-dimensional subspace spanned by the tangent spaces of the double point. The orthogonal complement to it is 2 dimensions, and what this is just it's a full Dane twist in that orthogonal complement, fixing the 2 tangent spaces. And so so that's exactly what this is. So you should think of this as like a generalized Dane twist type construction, but it's parametrized in general. Okay, so the family of diffeomorphisms of the barbell. So just from the nature of that construction, I claim that this diffeomorphism family is fiber preserving over an interval. So that barbell, the barbell, I'm splitting an interval out of the D2 factor, and I'm saying that if you take the projection map to the interval, this diffeomorphism family is fiber preserving, and it basically follows from the formula. The way this formula works is these vectors were chosen to be orthogonal to the 2-dimensional subspace that was spanned by the the tangent spaces of the double point. So this map, these are mirror reflections in vectors that are orthogonal to that 2-dimensional subspace. So that 2-dimensional subspace is preserved, and then maybe let's see. If we go back to this picture, right, that 2-dimensional subspace is preserved. So so there's this direction, this direction pointing towards the origin, from the origin to this resolution notation over here. That direction is the interval direction that I'm projecting onto, and so since that direction is preserved, these maps are orthogonal. That means the orthogonal complements are preserved. Yeah, and moreover, the orthogonal complements, when you look at F1 and F0, they always intersect that orthogonal complement in 2 points. So that is, a Euclidean space with 2 points removed. That is this factor split out of the barbell once you compactify or remove neighborhoods. Yeah, so theta is fiber preserving, and the fiber preserving diffeomorphism group of the barbell is, you can think about it. It's the loop space of the diffeomorphism group of dn fixing two disjoint subdisks. And you think about that a little bit more, that's homotopy equivalent to diff dn and some double loop spaces, the sort of a framing parameter of the dn's, and double loop space on Sn-1. This is sort of the diffeomorphisms are allowed to, in families, are allowed to, from the point of view of this homotopy equivalence, the disks are allowed to sort of orbit around each other. So these diffeomorphisms, they're, I guess you would think of them as sort of the braiding diffeomorphisms in some sense. And that gets to Victor Turchin and Paul Arnaud Sopmane's recent work. In low dimensions, every element in these low dimensional homotopy groups of barbell diffeomorphisms mod diff of the ambient disk has fiber preserving representatives. So what they do is they show that this is this quotient here is basically the loop space on a space of framed string links. And they've computed the low dimensional homotopy groups of spaces of string links. And so they know that in a certain range, the low dimensional homotopy groups all come from these braiding classes. So the fact that our barbell diffeomorphism is fiber preserving shouldn't be a surprise. I guess the nice thing is that it's just really explicit in a formula. So up to sign, I claim that our barbell diffeomorphism family, of course, in that splitting of the fiber preserving diffeomorphism group, there was this factor coming from double loops of the sphere, and that there's a very particular element here, the adjoint to the identity map on the sphere, right, where you move two suspension parameters over to double loop parameters. And I claim that is up to sign, that is our map theta. And the proof is actually not so bad. I'll give you an idea of why that's true, but this map, there's all kinds of nice ways of thinking about it. So that the dn here that splits the barbell into two solid tori, what you can do is you can ask what points on this disk are sent to E1 here and E2, right? Remember, this is a solid torus, it's a sphere across a D2. So this is a point cross D2 over here in that factor, and this is a point cross D2 in that factor. And you can ask, so which points on this barbell, on this thing that we call the mid-ball, get sent by this diffeomorphism family to E1 and E2 respectively? So those are disjoint submanifolds of the parametrizing sphere across dn, right? That mid-ball, and they're so this map is characterized by those two manifolds being linking. So that's one nice characterization of it. So it gives you a lot of freedom in terms of thinking about what's important about this family theta, and so you can even go further, and you can sort of describe that family rather explicitly. So that sphere. So what am I saying? So we've got an Sn-3 parametrizing this family of diffeomorphisms, and Sn-3, and so what did I say that? Sn-3, right? And then we've got that dn parameter family. So there's a Sn-3 cross dn, and what I want to do is I want to think about so what am I doing here? My brain got a little bit derailed. Give me 1 second to catch up with myself. Sn-3 across the mid ball, that's a dn. So that the two things together, that's 2n minus 3-dimensional space. Whoops. Yeah, and I want yeah. So that that dn, I'm going to think of it as a dn minus 1 across an interval. So I'm going to think of it. What happens to these interval? What happens to the intervals under that diffeomorphism? This interval fibering of the mid-ball, and so I get this picture here of a dn minus 2 across a dn minus 2 of embeddings of the interval into the barbell, and so I claim what's going on is you take that these intervals of the mid-ball, so they're generally straight, but curl it up like this, and you grab these two strands and you swing it around that sphere, grab these two strands and swing it around that sphere. That's sort of how you describe that family of embeddings. So you get this picture like this of the family of embeddings of the interval. So in more detail, that mid-ball, the dn, we split it as into an interval across a dn minus 1, so that this 2n minus 4 parameter family of embeddings, we get it from the spherical family of embeddings of the disk, and then there's a dn minus 1 coming from the fibering of the mid-ball, and so that gives you a map out of the smash product of these two spheres to this embedding space. And so I claim that if you in those embeddings, you look at what they do to pairs of points on the interval, there's algebraically just one pair of points. I mean, it's technically, I think, 4, but algebraically, there's, if you count them up to sign, there's just one pair of points where, technically, sorry, 3. There's 3. One pair of point algebraically where the first point is sent to E1 and the second point is sent to E2. It's a fun exercise. So this is much like working with Dane twists, like with the pure braid group, but with lots more parameters. Yeah. So the claim that these barbell diffeomorphisms are given by the adjoint to the identity map on the sphere, basically the way that works is both these families, capital theta and the induced family of diffeomorphisms coming from that adjoint, they're given by an isotopy extension process. And so the idea is, well, just compare the underlying motions, right? The embeddings, the embeddings of this, F1 and F2 that we used to construct theta, they came from this resolution construction. So those are all fiber preserving embeddings when you project to this coordinate. So you can really think of them as loop. Instead of embeddings of 2 intervals, you could think of it as a loop in the configuration space of 2 points in this Rn minus 1. And then once you have that perspective, you can just compare the two, and you get this, you get this, the identity map here. It's adjoint. While it's not that map, this is basically almost the same map in double suspension coordinates, but with some sign changes and some linear algebra going on. So up to some sign change, they're the same map. Yeah. So that's the local model for this family of diffeomorphisms. So we've got the local model of the family of diffeomorphisms of the barbell, but we want to know what it is as a diffeomorphism of S1 cross Dn. So we have this picture where we have it controlled in that little blue barbell here, but that's not really as a diffeomorphism of S1 cross Dn. So what we do is we're going to straighten the embedding F and muck up the isotop the barbell to. So what we do is we pull that loop back, and then we get this picture where the embedding now is straight and the barbell loops around like that. And now, since this orthogonal this factor here is Sn, that sphere here, you can just loop around and drag it to the other side. And so the barbell is embedded in this sort of cute way, like that. And now we can think about, okay, well, what is that? So we want to think about what does that family of diffeomorphisms of S1 cross Dn do to this disk here? Well, because of that picture we had with what the barbell did to the barbell diffeomorphism did to the mid-ball, we can make the exact same picture here with what it does to the a point cross Dn. Because just these points, so, these intervals here in, we're fibering the Dn as an interval across Dn minus 1. Most of these intervals are disjoint from the barbell, this funny embedded barbell. So the diffeomorphism does nothing out here, but when it crashes through the barbell, it's going to do what the barbell diffeomorphism did inside the barbell, but now it's got this funny embedding. So as you crash through, it's going to, 2 strands are going to race up and 2 strands are going to race down. And the ones that race up are going to sweep around the sphere over here. The one that race down are going to sweep around a sphere over here. And so here, these dots here, I'm depicting, those strands race up, but they crash through the altitude of the sphere that's wrapping around. So you get this funny picture here. This is with the S1 factor suppressed. You can depict this in many ways, but this is maybe the cutest picture of what that family looks like. Yeah. So the rational homotopy groups of embeddings of an interval in S1 cross Dn, the first 3, there's dimension 0 because it says path components because the interval can go around the S1 factor. There's the n minus second homotopy group, and that comes from these double point counts. And then the next rational homotopy group is in dimension 2n minus 4. One of the things we really need to do, David, when I say that I mean David and I need to compute this group exactly, and we're pretty close to having it rationally right now, and I'll hopefully maybe give you a picture for that. Let's see. So yeah, so pi n minus 2 is it's the elements of it are distinguished by a double point count, a type 1 Vasiliev invariant, and the invariant that we use in the next homotopy group is sort of a type 2 Vasiliev invariant, and it's a type 2 Vasiliev invariant, a variation on something that I studied in grad school. So we're going to look at geodesics in S1 cross Dn that intersect embeddings in precisely 4 points. So I'm thinking of S1 cross Dn as just being flat with its standard metric, Euclidean metric. So what do? Given something in pi 2n minus 4 of embeddings of an interval in S1 cross Dn, you lift it to a Z equivariant family of embeddings of Z cross I and R cross Dn. And so the invariant it's going to be, I guess I'm lying a little bit. It's going to be a little quotient of this thing, but it's going to be in a Laurent polynomial ring with 2 variables. And we're counting straight lines in R cross Dn that intersect the embedding at 4 points. We're going to demand that 2 points, if 2 points are consecutive along the parametrization, right, so since this is equivariant for a moment, just think about a single strand here, 0 cross I. If 2 points are consecutive along the parametrization, they are not consecutive along the straight line in R cross Dn. And we also demand that the outermost pair of points come from a common lift. For knots in R3, this is a description of the type 2 invariant. So you could call them 3, 1, 4, 2 quadrisequence. That's the terminology I had when I was a grad student. So here's an embedding of an interval in R cross Dn, and standard on this side, standard on that side. This is a type of straight line we're talking about. For the figure 8 knot, there's 3, and anyhow, that's the kind of thing that I'm talking about. Yeah, so W3 should be thought of as something that's cooked up to count Whitehead brackets. And let me tell you what I mean, because it's hard to make sense of it otherwise. So if you take triples of points in an interval, so those are in the interval, and we look at the corresponding points under a particular embedding. If we got a lift of an embedding of an interval in S1 cross Dn. So there's this collinear triples that I call co1ab, and oh, I messed that up. Sorry. This should have been co3ab, and that's co1ab. So because here there's the triple that are on a straight line, and this is the ordering along the straight line. I meant to say, I meant to switch these definitions. Sorry about that. That's a typo. Whoops. So there's P1, P2, and P3. And so T to the alpha means, use a covering transformation, a covering transformation of R cross Dn as a covering space over S1 cross Dn. So we've got these triples are on a line in that form. And I could maybe even switch. Well, I won't fix that right now, but I'll fix it at the end of my talk, I guess. Yeah. So these triples, if you think about it, they do detect elements of the pi nth homotopy group, pi n homotopy group of configurations of 3 points in S1 cross Dn, and the thing is that these geodesic quadruples, they are a count of overcrossings of co1 alpha beta over co3 alpha beta with respect to the T2 coordinate. So you're thinking about them as living in this spherical family cross C3 of an interval, which is like a tetrahedron. Yeah. So these are designed to count Whitehead products in that sense. So this is the most this is the least well documented in our paper draft right now. I'm arguing that this W3 invariant is well defined, and it's almost well defined in a really direct way. So you take a one parameter family of spherical families of these embeddings, and you want to know, do these geodesic quadruples run off the boundary? So so just imagine that you have those geodesic quadruples running off the boundary. If at that degenerate time where it runs off the boundary, the line projects to a line in Dn, the line in R cross Dn projects to a line in Dn, well then the ordering along the line is preserved. And just by the way we chose it, right, if you're consecutive along the embedding, you can't be consecutive along the line. That would be impossible. So right, because points one, to run off the boundary, points 1 and 2 would have to come together, but they're not consecutive along the line, so it can't happen. So the only way you could have a quadruple run off the boundary is if the line projects to a point in Dn, if the line is vertical in that S1 direction. And unfortunately, this can happen. And so we have to worry about the behavior of the family on the boundary. That requires a correction term. So let me digress a little bit about the models that we use in embedding calculus. So there's this mapping space model that I'm using due to Dev Sinha. I choose it just because it's very geometric, and I think this work is going to appeal mostly to very geometric people. This is maybe not most people's preferred model for working with embedding calculus. So it's this thing called the mapping space model. What you do is you replace the space of embeddings of an interval in a manifold with a space of mappings of a compactified configuration space of the interval to a compactified configuration space of the target manifold, and the configurations are allowed to have unit tangent vectors. So Cn is this Fulton-McPherson compactified configuration space of distinct n-tuples in the manifold M. The Cn prime, it's the pullback of the unit tangent bundle to the configuration space, unit tangent bundle to the nth power. And the most important feature of this mapping space is that the mappings are supposed to be stratum preserving. That means if, like, say, point 1 and point 2 collide in the interval here, that's what the compactification allows, then they also have to collide, point 1 and point 2 have to collide over here. And the maps are aligned in the sense that when point 1 and point 2 collide, well, they have unit tangent vectors associated to them, but in the compactified configuration space, you have an infinitesimal displacement vector, and that has to coincide with the velocity vectors of these points. So that's called the nth stage of the Taylor tower in this mapping space model. And because the configuration space of an interval is basically a glorified n simplex, this is like a it's called the Stashev polytope. That means that this embedding calculus is like a multi-relative homotopy group, right? That that embedding space for certain purposes, it's really just this mapping space of a simplex of the right dimension into this configuration space of points in S1 cross Dn. And so in our case, it suffices for this homotopy group, it suffices to compute the third stage, so maps from a tetrahedron into this configuration space. And the second stage, the pi 2n minus 4 of the second stage, it's a cute argument that that's a torsion homotopy group. So when you have these maps, these third stage maps corresponding to elements of pi 2n minus 4, the idea is rationally the maps on the boundary, those are second stage, the S2n minus 4 across C2. The boundary facets of this tetrahedron are triangles. Since the second stage, the homotopy groups are all torsion, rationally you can just sort of cap off the tetrahedron and turn it into a ball. And so that gives you an element, so that gives you this homotopy group is sort of an appropriate subquotient of pi 2n minus 1 of the configuration space of 3 points in S1 cross Dn. And because this configuration space is basically, it's homotopy groups split as a product of the Fettel-Neuwirth fibers, and those are S1 wedge Sn wedge Sn cross S1 wedge Sn cross S1. So pi 2n minus 1, it's just generated by Whitehead products rationally. Yeah, so that's the rough idea of how you would try to prove that this W3 is well defined. You have to control those correction terms coming from exactly what additional what Whitehead products are preserved after you do that capping off construction, and that's controllable. And so this family of embeddings is schematically, when you lift to R cross Dn, you get this kind of picture, right? So here's the zero lift. It's this sort of S type thing here, and then there's all the translates of it. And so that family is schematically that way. And I like to think of it as like this equivariant infinite stranded Borromean rings. It's sort of you want to try to show that it's non-trivial in that sense. And so the nice thing about this family is the geodesic quadruples, where the two extreme endpoints are on the zero lift. They all appear in this pink region, and that's sort of a delicate geometric argument. And so you can just but if you believe that, you can just sort of sit down and count them, and there's a formula for them. So like for theta 2, it's this simple formula. For theta 3, it's this. In general, it's sort of clunky. And there's a lot of cancellation, but there's this stuff that survives. And so, provided you believe this, and I don't expect you to, but it's just a sketch of the argument of what you do. Provided you believe that gives you as a corollary, there's the maps from embeddings of S1 to S1 cross Sn. There's the fibration to diff of S1 cross Dn, and then there's this map to embeddings of, well, it's also a fibration, I guess, to embeddings of Dn and S1 cross Dn. And in this range of dimensions, that composite is faithful for all n greater than or equal to 3. So that's a sketch of the argument of how we're piecing things together. So there's some cute observations. The operation of lifting a disk to a finite sheeted cover of S1 cross Dn, that's an endomorphism of these groups, provided n is greater than 1. When n is 1, is sort of a degenerate case. It's because the boundary sphere is not connected. The fixed points provided m is greater than 1. It's a subgroup isomorphic to pi0 of embeddings of dn and dn plus 1. And this is sort of the most important group from the point of view of the Schoenflies problem. So this is embeddings of dn and dn plus 1. That's the standard linear embedding on the boundary. And what do I mean? So pi0 of this space of embeddings is isomorphic to pi0 of embeddings of Sn in Sn plus 1. So the Schoenflies problem asks if every embedding of that sort is in the image of this inclusion, right? If every embedding is just a reparametrization of the standard linear embedding. So our theta k examples, when you lift to a sufficiently high theta k, when you lift it to the k-sheeted covering, it becomes trivial, and that stems from these kinds of pictures, right? When you go to the k-sheeted covering, this whole embedding family, there's a disk that it does not pass up here. It's like it's sitting in a ball, and yeah, so it becomes trivial there. Yeah. So where was I? So yeah, the Schoenflies problem, how our examples don't impact it, but are kind of nicely close to it. Oh yeah. So earlier we noticed that the space of embeddings of Dn in S1 cross Dn, it has this homotopy type of this space of unnotable embeddings of a codimension 2 disk, or there's a loop space parameter, and there's this unit normal vector field parameter. So if we just go with that for a moment, so we know that this homotopy group is not finally generated. So because there's that homotopy equivalence there, we know that in one shifted degree, this homotopy group of this embedding space is not finally generated. And now there's that framing parameter, but so there's a fiber bundle from, let's see, from this space to this space where you forget the vector field, and the fiber of that fibration is just a iterated loop space on S1. So that's a contractible space. So this space and that space actually have the same homotopy type for us, which is nice. So this embedding space is not finally generated. And this embedding space, you can relate it to this, the embedding space of a codimension 2 unnotable sphere in an ambient sphere by, there's a stereographic projection construction which says that this space and this space basically differ by, in a bundle sense, they just differ by a Stiefel manifold. So Stiefel manifolds have finally generated homotopy groups. So since that's not finally generated, this is not finally generated. So what does that say? So codimension 2 unnotable embeddings of the 2 sphere in the 4 sphere, its fundamental group is not finally generated. Yeah. So Alan Hatcher has shown that the unnotable embeddings of the 1 disk in the 3 disk, that it's contractible, or equivalently the unnotable embeddings of S1 and S3, it has the homotopy type of the round circles or the great circles, which is also a Stiefel manifold, or because we're in S3, it's S3 cross S2. Yeah. So Hatcher's result is very different to what we're talking about. We're saying that you don't have anything like that happening. And I want to conjecture how to interpret the Hatcher-Wagner 2 torsion. So given an embedding of dn in S1 cross dn, you can fiber that dn as a dn minus 1 across an interval. So that gives you a map from Sn minus 1 to the embedding space of an interval in S1 cross Dn, this group is two torsion, and I believe it's not finally generated. I guess I haven't proven that. So so I believe the way that this is two torsion is, so in pi n minus 2 of this embedding space is rationally, infinitely generated. What you do is you precompose those elements in pi n minus 2 with a suspension of the Hopf vibration, and I believe that would give you all the generators of pi n minus 1 of this embedding space. And so what I think is likely true is that these Hatcher-Wagner embeddings, you detect them by fibering them and looking at this family of embeddings of an interval in S1 cross Dn that you get. But it just rhymes so well with everything we're doing. This is a natural conjecture, and maybe David will join me in conjecturing this eventually. I think that's everything. So I hope I didn't go too far over time.
Okay, so let's thank Ryan for that very nice talk.
Thanks for having me.
Are there any questions, comments?
Yeah, Ryan, I'd just like to ask a general question.
Yeah.
It doesn't seem in this analysis there's much room for dimension 4 to look special. It looks like all higher 4 and higher dimensions in this analysis seem to come in on sort of an equal footing, and I just wonder what your comment is on that.
Yeah, there's some aspect of that, but in the stuff we're saying, in higher dimensions, the stuff we're saying is about higher homotopy groups of these embedding spaces and diffeomorphism groups. So there are ways in which, if you peel back the analysis a little bit further, for example, if you go up, instead of the in dimension 4 here, we're talking about the second homotopy group of embeddings of an interval in S1 cross Dn, but the third homotopy group, so sort of the next non-trivial homotopy group of that embedding space, there are elements of it that are peculiar to dimension 4. When you go to S1 cross Dn for n larger, the third non-trivial homotopy group, it doesn't have, well, maybe in dimension 4, there's sort of a mixing of two elements of the Taylor tower coming from sort of two different layers. But in higher dimensions, that mixing of the layers doesn't happen in the third homotopy group. So there's still lots of, I think there's still lots of room here for dimension 4 to be special. Yeah, the way dimension 4 is special here is that it's the only dimension where we're getting sort of pi 0 information.
Well, okay, let me ask the question this way. Is there some potential analog in dimension 5, perhaps in parameter families, of the fact that there are uncountably many structures on R4? In other words, your answer seems to be that perhaps if you ask questions in higher parameters, you'll get similar answers in high dimensions as in lower dimensions, but that doesn't sort of fit with my experience. That's why I'm puzzled a little bit.
There's a lot here that's still pretty mysterious to me. I'm not sure if I have a good answer to your question. There's definitely things that are peculiar to dimension 4 here. The analysis that we get, the kind of things that we get in higher dimensions, where like smooth structures on R4, I wouldn't even know where to start to relate this to that kind of thing. But maybe that wasn't really your intention.
Well, or what about just the fact that even on compact four manifolds, you can have countably many smooth structures on you know, the homotopy type of the Kummer surface or something like that. I mean, we see it's connected to the Schoenflies problem, perhaps. I mean, in terms of
Right. So
your discussion is already potentially impinging on counting smooth structures, and we just know that from existing techniques how different the answer is in dimension 4. So I'm just wondering what to think about that. You know, how should I think about that?
I can tell you some things, like, for example, the Taylor tower, it does depend on the smooth structure of the target manifold. There are results about sort of in dimension ranges where, like, you know, rationally it may not depend. It's, you know, homotopy groups rationally in a dimension range may not depend on the smooth structure of the target manifold. There's certainly, like, getting these techniques to apply to various different manifolds. The fibration sequence that allowed us to just even to apply this to sort of statements about embeddings of things in spheres. I mean, they were rather delicate arguments, and I think if you wanted to make these kinds of arguments to other manifolds, like especially if you have interesting smooth structures, I mean, this embedding calculus, it's really sensitive to your handle structure on the target manifold. So, I don't see immediately any interesting collisions with what's known, but yeah, I'd be if you have some ideas for, you know, where this could cause some sort of pinch points between different perspectives, that would be great.
Yeah, no, I'll think about it. I mean, it was really a superficial question. I was just struck that in all your slides, it was always DN, you know, I mean.
Yeah. Right. There's this right, if you had like a non-standard disk, my analysis all goes haywire, but part of that is just artificial with, like, I chose a very particular geometric perspective. The Taylor tower would still work, but it would be it could potentially be very, very difficult to work with. There's other models for the Taylor tower where, instead of using these explicit models of devs, you use these homotopy limits of these sort of rather complicated diagrams. And those are, you can work with them, and they are kind of directly related to what dev is doing, but I find oftentimes just even doing fairly explicit constructions with them can be difficult, but that's peculiar to my own difficulties with the machinery.
Okay, thanks a lot.
Well, thanks for the comments.
Are there any other questions or comments?
May I ask two related questions, Ryan?
Yeah.
So to detect these families that you constructed in a homotopy groups of diffeomorphisms in pi n minus 3, you use this invariant W3 in pi to 1 minus 4 of the embedding space?
Yes.
Are the numerics correct?
Yeah.
So So you're evaluating on the Whitehead product of theta k with itself or something?
Right, so these invariants are meant to sort of detect Whitehead products. So yeah, the idea is this element of I should go back a little bit. Yeah. So you got an element of pi 2n minus 4 of this embedding space, right? So that came from you've got an element of pi n minus 3 of embeddings of the n disk in S1 cross dn, and then you fiber that as dn minus 1 across an interval. So n minus 3 plus n minus 1 is 2n minus 4. Right, and so now, so the idea is, so you've got a map from a 2n minus 4 sphere cross basically a tetrahedron into the configuration space of 3 points in this S1 cross dn. And so the idea is on the boundary sphere cross triangles, those maps, so it turns out for the maps theta k, those maps are just null on the nose, and we can write down an explicit null homotopy. So you've got this map from S2n minus 4 across the tetrahedron, and on the 2n minus 4 across the triangles, there's sort of a canonical null homotopy of those maps. So you basically close this map off to a map from a 2n minus 4 sphere across a 3 ball into this configuration space, and it's standard on the boundary. So with a little bit of work, the boundary goes to a base point. And so now it's just so that's essentially an element of pi 2n minus 1 of the configuration space of 3 points in S1 cross dn. The issue is, right, when you close off, you could close off in many, I said theta k has this canonical null homotopy, but then close off using some other null homotopy, and your element of pi 2n minus 1 of this configuration space changes. The issue is, you might get sort of different Whitehead products, and you do. There are some Whitehead products that appear and disappear, and so you have to be very careful about which ones you keep track of, and so there's kind of an interesting relationship where you've got Whitehead products of like common lifts of two of the sort of standard generators of the homotopy groups of the configuration space, where one point wraps around another. So common lifts of Whitehead products of common lifts, common positive lifts minus common negative lifts. There's a relationship between those and Whitehead products where you just lift in a preferred covering direction. It's a peculiar relationship, and it ultimately boils down to controlling the Taylor tower from the map from the third layer to the third stage of the Taylor tower to the second stage of the Taylor tower. So the connecting map in the homotopy groups of spheres, the connecting map in the homotopy Langevin sequence of that fibration is sort of what's telling us what's going on here. And that connecting map, it's non-trivial. It's not, but it's controllable. And so these geodesic quadruples are sort of keeping track of Whitehead products and sort of keeping track of them in a way so that you don't get confused by some Whitehead products that are sort of ambiguous under this closure operation. So that's the that is the ugliest part of our argument right now, and you can kind of get a sense with this geometric, so you have to deal with all the possible different null homotopies on the boundary, and since we're talking about linking of geodesic triples, that is a lot of geometry to process for this family of embeddings, right? So if you really think about it as like numerically, right, where we're solving families of quadratic quadratic algebraic varieties over this parametrized family of embeddings, which is it's a subtle thing, and doing it, trying to like just to visualize it all is pretty subtle, even though these are quadratic equations. They're not all that complicated, but still it's pretty complicated.
Is it easy to say what the idea behind defining this invariant W3 is, with counting lines with certain properties?
I tried to say it earlier, but it was, so there are these submanifolds of you think of the parametrizing family, the S2n-4 being around, but you look at triples of points in this tetrahedron where the points, so P1, P2, P3 are the points under the embedding lifted to the universal cover, where we're looking at triples of points where the relevant covering transformations are linear. So and so these classes detect elements of pi n of this configuration space. So from the point of view of framed, from like Pontryagin's, from his point of view on homotopy groups, the Whitehead product, when you're mapping to wedges of spheres, Whitehead products are detected by linking numbers of manifolds, of disjoint manifolds. These manifolds are disjoint when you're thinking from the point of view of the parametrizing sphere across triples of points in the tetrahedron. These are disjoint because, well, P2 is on the right-hand side of those two, and P2 is on the left-hand side of those two. So in this manifold, P2 is on the right-hand side of that geodesic triple, and on this manifold, P2 is on the left-hand side in that geodesic triple. So these manifolds by design are disjoint, and they do detect all the elements of pi n. They're disjoint, they detect all elements of pi n, so their linking numbers have to detect Whitehead products from this sort of framed cobordism perspective. And their linking number is exactly, the linking number before you close off is exactly these geodesic quadruples of this special type. So the issue is the geodesic quadruples are counting these linking numbers modulo the issue of there's the potential for some of them to run off the boundary. And when you get to the boundary, right, like if P2 and P3, if T1 and T2 collide, that means P1 and P2 are the same. But if alpha isn't 0, this is in a different covering transformation. So the 2 points are P1 and P2 are macroscopically the same, but you've translated P1, so it's vertically displaced from P2. So you're talking about geodesic triples that are vertical. Right? So that's why there's this issue of the vertical triples for the correction term, and that's why this correction term is kind of subtle to compute. I hope that helps. That's not a full explanation, but I would really love it if there was some. It would be great to have an alternative machine that would confirm these computations from, say, a more algebraic perspective. If there was some nice machinery from rational homotopy theory where you could do the analog of these closure operations and see which and to detect after you close which Whitehead products are exist in our our maps are essentially homotopy groups of these configuration spaces. So they're in this dimension range where they're all Whitehead products. So which Whitehead products come up? It would be nice to be able to verify it an independent way, because our argument is very geometric, and I'm guessing a referee is going to be not. Most choices of referees are going to want an algebraic argument.
Ryan, have you taken a look at the work of Thomas Wilbacher? And
Is there a particular, like, so?
yeah, maybe the I think maybe
Like,
that paper with Turchin and Benoit Fraisse.
so the one that Victor talked about this morning?
I was not there, but maybe.
Oh, okay. All right. Yeah, there's an embedding space seminar. And
Oh, I
think
see.
Victor talked about it this morning.
Yeah.
Unfortunately, they operate on European time, and it's way too early for me.
I see.
Okay,
So
but
there are techniques there that that are useful for you, I think. They even
Okay.
describe like the higher brackets combinatorially at the chain level.
Okay.
Yeah, that seems.
I'll look at it. Hopefully there is some useful machinery that can sort of independently. We like this argument here. This is one thing. We're also trying to develop a secondary argument. This invariant in dimension 3. This invariant is this count of geodesic quadruples of knots in R3. Misha Polyak had a really beautiful argument that there's another formula for this where you just look at planar diagrams of your knot and you count pairs of double points in your planar diagram. There's some combinatorics involved, but you get something called a Polyak-Viro formula for this invariant. And so I've been trying to do the analogous argument to get a Polyak-Viro formula for an analogous W3 invariant that could maybe distinguish these classes. Unfortunately, the correction term for it is far worse, and there's even more problems because the Polyak-Viro formula is using it uses it's only looking at pairs of points that project to a common point under a fixed direction, and what that means is that it's not really a literal. It's not really a literal. It's not counting a linking number for disjoint manifolds, so it's not as directly related to Whitehead products. So it gets into this murky area where you've got manifolds that are maybe not always disjoint, but they're often disjoint, and elements of how they link is preserved under families, but not some aspects of how it links is preserved and some aspects of how it links is not preserved. And so it's rather murky stuff where I don't know enough homotopy theory to really control what's going on there. But there is a possibility that we could recover maybe a very similar invariant using that type of construction. We have not been successful with that yet. But the nice thing about that is that because it's only counting double points in diagrams, it's a much more diagrammatic construction. So it's very close to being a really simple thing to count. Whereas the W3, this geodesic quadruple correction term, it is not very combinatorial. It's very geometric. I might find a way to represent it more combinatorially, but it's in the way we're working with it right now, it's very geometric, unfortunately.
Okay. So the paper is called Under Rational Homotopy Type of Embedding Spaces of Manifolds in Rn. I can send you the link.
And it's Wilbacher, Turchin, and Fraisse. Is that right?
Yeah.
Okay. Okay. Yeah.
Oh.
I've been meaning to read that paper. That would make Victor happy if I read it. Yeah.
Are there any questions? More comments? If not, let's thank Ryan one more time.
Thanks for having me.